Thank you for joining us today. The title of this presentation is Climate Variability Induced Shifts of the Wave Climate in Mexico. The research was carried out by Thomas Mortlock of Risk Frontiers and Rodolfo Silva, Ichazo Oderis and Ismael Mariño of UNAM. Interannual variability of wave climates can increase or decrease seasonal erosional risk. So, understanding how long-term variability affects the seasonality of sediment transport is important in risk assessments. There have been many attempts to quantify long-term variability in offshore wave climate, as this is the primary driver of coastal processes on sandy coasts. However, there is very little work on how the long-term variability of wave climate influences sediment transport. The mean wave direction of incoming waves is one of the most important drivers of sediment transport, but this is not yet fully understood. In 2015, Barnard et al. Found the El Niño Southern Oscillation determines the vulnerability of Pacific coasts. Several works at global scale have found that ENSO is the climatic driver that most affects the interannual variability of the wave climate, but how ENSO impacts wave direction is still not fully understood. In July 2020, huge waves pummeled beach suburbs north of Sydney. Some coastal areas were severely eroded and homes were at risk of collapse. The extreme sea state was caused by a strong low-pressure system. Waves as high as 11 meters were recorded. This is about 4 times the size of an average wave at this time of year. These pictures show how the storm surge ate under houses, leaving the foundations exposed. Normally, in the Mexican Pacific, the large swells generated in the southern hemisphere appear in the summer months. However, in 2014, in mid-spring, associated with an unusual El Niño event, much of the Mexican Pacific coast experienced erosion and major flooding. In recent years, the variations in wave climate conditions, particularly the period and direction of the waves, have drastically shifted the orientation of sandy shores on the central Mexican Pacific. The objectives of this work were to analyse the impact and variability of the different types of wave climates on the coasts of Mexico and study large-scale phenomena in regional areas to facilitate the study of wave climate variability and climate change. In 2020, Oderis et al. Classified wave climates into extratropical, subtropical and tropical. Different mechanisms in the lower structure of the atmosphere generate these distinct wave climates, and large-scale atmospheric phenomena can be detected. The classification employs the K-mean and the wave direction and wave power monthly averaged. ERA 5 reanalysis was used with hourly data and 0.5 degrees by 0.5 degrees spatial resolution for 1979 to 2018. The global wave climate types represent the wave generation systems responsible for wave energy conditions. A multivariate K-means clustering technique was used, which clusters wave powers and wave directions. This gives a monthly index for each grid cell for variability of each dominant wave climate type over approximately 40 years. Since monthly means were used, for the directional wave climate, variations of less than a month were disregarded. While more than one wave climate type may be affecting a single grid cell in any given month, the subdominant wave conditions were not analysed for the variability of each grid cell. The three global scale wave climate types identified are the extratropical westerly, the subtropical southerly, and the tropical easterly. The coast of Mexico is directly influenced by these three global wave climate types. Classified by dynamic clustering, the seasonal variability of the three planetary wave climates are shown here. The wave power is shown in kilowatts per metre, the yearly average A, D and G, winter averaged B, E and H, and summer averaged C, F and I, of the westerlies at the top, easterlies in the middle, and southerlies below. The results show that each wave climate has a similar directional wave power regardless of the season. Looking at the panels B and C, in winter these low pressure centres predominate, producing higher pressure gradients, well-defined wind belts and stronger surface winds. In panel E, in the northern hemisphere, in winter, the polar easterly winds and waves intensify and extend, dominated by the Aleutian and Icelandic lows. Panels H and I show that the low and high pressure belts create the subtropical and subpolar southerly winds, which in winter intensify subpolar wave climates, whereas in summer lead to intensification in wave power. The present research is in line with previous findings. We hope that details of the methodology used and the results obtained will soon be published. This slide shows the mean wave power on the Mexican coast for each wave climate type for winter, A to C, and summer, D to F. This figure shows the contribution of each wave climate type to the mean wave direction on the Mexican coast for winter, A to C, and summer, D to F. For the direction of the waves, we used the meteorological convention. Overall, the results show that the Mexican Pacific coast is impacted by both extratropical westerly and subtropical southerly wave conditions, with considerable seasonal variation, while the Atlantic coast is influenced by the tropical easterly wave climate all year round. The results of this work indicate that the wave climate of the Mexican Pacific coast is predominantly bimodal, consisting of a westerly wave climate type with its origins in the North Pacific extratropics, and a southerly wave climate type generated in the Southern Ocean. This bimodality has considerable seasonal variability. Conversely, the wave climate of the Caribbean coast shows significantly less variability in directional wave power, with the wave field generated in the Atlantic tropics all year round, with much less latitudinal variation. The classification presented here quantifies the directional wave power associated with atmospheric origin. This information could be used to better manage our coasts under climate variability and climate change. Thanks for listening to this presentation. If you have any further questions, please contact any of the authors by email. Thank you, Chair. Any questions?